For the first week of the synthesis of lidocaine, the procedure was as follows. We began the experiment by obtaining all the necessary equipment. For part 1 of this synthesis, we will need a 3 milliliter graduated disposable pipette, 25 milliliter Erlenmeyer flask, a 10 milliliter graduated cylinder, a 20 milliliter beaker, 400 milliliter beaker, a 25 milliliter sidearm flask with the vacuum tubing, ring stand, and micro scale clamps, a Corning stirrer hot plate, and a 100 to 1,000 microliter pipette, as well as a 20 to 200 microliter pipette. For the chemicals, we will need 175 microliters of chloral acetyl chloride, 242 milligrams of 2,6-dimethylaniline, 600 milligrams of sodium acetate dissolved in 8 milliliters of DI water, and around 2 milliliters of glacial acetic acid. For the first step of the experiment, we weighed out 243 milligrams of 2,6-dimethylaniline, then adding around 2 milliliters of glacial acetic acid, and finally adding 175 microliters of chloral acetyl chloride, all into the 25 milliliter Erlenmeyer. When this mixture was lightly swirled, the solution turned a pink color. The mixture was then placed on the hot plate setting of around 2 to 3 for about 4 minutes. After adding sodium acetate solution, which was used instead of preparing solution of 600 milligrams sodium acetate in 8 milliliters of DI water, the solution became cloudy white, and a gas precipitate was also formed. This solution was then placed in an ice water bath for around 5 minutes. During this time, white solid crystal precipitate began to form in the flask. We then assembled the vacuum filtration. This was done by first obtaining the proper equipment, including a Hirsch funnel, 25 milliliter sidearm filter flask, and a filter paper to fit the proper funnel. Before running the solution and precipitate through the funnel, we made sure that we clamped the filter flask to the ring stand, connected the red tubing, and turned on the vacuum, and then ran the solution through. After this, we examined the crystals of the product. The solid precipitate formed was white crystals, and we then placed this solid filtered product into an initial tarred aluminum dish, gently scraping the solid away from the filter paper using a micro spatula. Finally, we passed in this product in the aluminum dish into our instructor. In this first step, the limiting reagent for part 1 was 2,6-dimethylaniline, and this can be proven by going through our theoretical yield. So here we start with 243 milligrams of 2,6-dimethylanilide. We then multiply that by 1 millimole of 2,6-dimethylanilide and then divide it by its molar mass of 0.12118 milligrams. We then multiply that by our molar conversion, which is 1 mole of N2,6-dimethylphenyl chloroacetamide divided by 1 millimole of 2,6-dimethylanilide. We then multiply this by N2,6-dimethylphenyl chloroacetamide's molar mass, which is 0.19766 milligrams. And then we get a grand total of 396 milligrams of N2,6-dimethylphenyl chloroacetamide. We can tell this is the limiting reagent because when we do the theoretical yield conversion of chloroacetyl chloride, we get a larger number. So if we go through this theoretical yield calculation, we start with 249 milligrams of chloroacetyl chloride, and then we multiply that by its molar mass, and then we multiply that by the molar conversion again of N2,6-dimethylphenyl chloroacetamide, which again is 1/1 because we had a 1-to-1 ratio. And then we multiply that by N2,6-dimethylphenyl chloroacetamide's molar mass again, and we get a grand total of 436 milligrams, which again is a larger number. So because this one has the smaller amount, we call it the limiting reagent. In terms of the new functional group that was made in the first step, we made an amide, which again was N2,6-dimethylphenyl chloroacetamide. And this can be proven by observing the IR spectrum. We see here that instead of a primary aromatic amino stretch present, which was present before, we now have one NH stretch at the 3,180 centimeters to the -1, which is indicative of a secondary amide. During liquid-liquid extraction, Hydronium chloride acted as the acid, which then added a proton to lidocaine, which then produced lidocaine hydrochloride through an acid-base reaction, which is shown right here. And you can see right here how this hydronium chloride adds this proton onto that nitrogen, forming lidocaine hydrochloride in water. And then we have potassium hydroxide acting as a base, which then removes that same proton from the lidocaine hydrochloride through an acid-base reaction, again, creating the lidocaine-free base, which is much more soluble in water due to the lack of that proton that was removed, interfering with the water molecules that are present. You can see right here that this proton present is removed by potassium hydroxide, and we get a tertiary amine in the lidocaine-free base.